let's continue with our discussion. Let me give you something very important, the relationship between potential and electric field. Let's talk about potential derived from electric field. Potential from electric field. So let's remember the change in the potential energy. Change in the potential energy was negative of the work done by the system. Do you agree with this? This is the work done by the system. If you take the negative of that, it gives you the change in the potential energy. Do you understand this? Yes? So what happens if I divide both sides by Q? Okay? Provided that this is the force due to the electric field. This is the force due to E field. That's what we are assuming here. And if I put a test charge on this system and divide everything by Q, so divide by Q, which is the test charge, and what do you get? The formula that you will use many times. This is the formula. VB minus VA is equal to minus integral from A to B E dot dx, or in the electric field section we just call it dl. Okay, so this is the formula. How did we get it? We just remembered that force divided by test charge is electric field, and potential energy divided by charge is potential. Any questions, comments, ideas? No questions? So if you remember, we already discovered the potential due to a point charge. Let me ask you if you remember it or not. For a point charge, let's say you have a point charge here at a distance r. Do you remember the potential? VR? Anyone? KQ over R. Everybody agrees with this? Yes? Now the question is, what if you have, for example, a potential, find the potential of a conducting sphere. Find the potential of a conducting sphere with a uniform charge distributed throughout its surface. So it has uniform charge plus Q. It has to be at the surface because of the material property. It's a metal. All charges go to the surface. It has a radius r, right? So what you are going to do in this kind of problems, so let's say you want to find the potential over here. If you want to use this formula, right, you need to integrate over all the tiny elements of charge. Do you understand what I mean? Because you only know potential due to a point charge. However, there's an easier way to do this. What is the easier way? The easier way is to use the other formula, this formula. So to use that formula, to use this formula, you need to first find electric field, then go from electric field to the potential. So far so good? So I want to find electric field outside. Let me call this point A, and let me call the point B to be at infinity. Okay? So what I do is I first write down the formula. I know that if I know that VB minus VA is negative integral of E dot dl. Okay? In this particular case, I'm going to go from, let me just define some x at a distance x. I have some dx. And this dx points this direction. Electric field is also pointing in that direction. And I can just take the integral. But first, I need to know how electric field changes with x. Are you following? So we are putting together lots of ideas. I hope you are following. How did we find electric field because of a uniformly charged metal? What did we use? Gauss's law, yes. So you use Gauss's law, E times 4 pi x squared equals Q enclosed, which is just Q over epsilon 0. So you get yourself the expression for the electric field. Right? Now you use this expression to write down VB minus VA is equal to minus integral Q over 4 pi epsilon 0 x squared dx. Did you follow all this? Let's put the boundaries. VB is at infinity, so VB at infinity is 0, minus VA, which is potential at R, equals integral going from R to infinity, Q over 4 pi epsilon 0 x squared dx. Everything is clear here? Yes. Yes. The R to infinity part. Very good question. So, what was your name? Sorry? Onat. Onat. Look, we are going from A to B. And A is the point where the distance is R. Okay? And we are going from that point, which is at a distance R, all the way to infinity. Okay? What was your question?
Why do we have to choose dx in between A and B? And why did we choose that?
So we need to choose, we need to integrate, first of all, because electric field depends on the distance. That's number one reason. Number two is, your other question is, do we need to choose x between A and B? Not really. The more important thing is to choose x wherever E has just one formula and the formula is not changing. You know, like I'm defining E with this formula, but this formula works only outside. Remember, inside it will be 0. Okay? But I'm taking the integral, both my A and B are outside, so I can use just one formula. If the formula changes midway, then you cannot take just one integral, you have to take integral up to the point where one formula works, then another integral up to the part where the other one works.
B is at infinity, right?
B is at infinity. Yes.
If the system is not symmetric, then it's better practice to directly integrate for the potential V, or just is calculating.
The system will never be not symmetric, but say it again, please.
Like
So don't worry.
So
Yes.
Gauss is, if you don't use Gauss, then you can still calculate.
The formula is still correct, but the electric field is so distorted probably that you won't be able to find integrals anyways.
Yani direkt B'yi bulmak lazım, o zaman
No, it's still worthy to find E first. And then, well, your question involves, I guess, numerics. Is that the case? Like, if it's just a shape and you are a computer scientist working in the midst of computer science and physics, is that the thing? Maybe. Then you have numerics, you can do everything. You can even take the integral of, just point integral of kq over r, if that was the question. Okay? So here we are trying to find solutions analytically, right? And this is the way to go. Find the electric field first, take the integral of the electric field. Good. So let's take this integral and let's be careful with the plus and minus signs. So first of all, I would like to just say that this is going to be plus, like this. So VR is this integral q over 4 pi epsilon 0 dx over x squared r to infinity. This is basically integral, no, let's take the integral already, minus 1 over x, evaluated at infinity and r. Do you agree? Which is 1 over infinity minus 1 over infinity minus 1 over r, which is 1 over r. So VR, after all that trouble, we get the same result as the point charge. As it usually happens with spherically symmetric things, right? You get the same result as the point charge. Let me just make it nicer. All right. Do you have any questions? No? Now, we are not done with this problem. We have found potential outside the sphere. So let me just write it like this. We have basically found VR greater than R. What if we are inside the conducting sphere? Okay? So what happens inside? So far, we have found the solution for outside, and our formula extends till this point, where V of R is equal to Q over 4 pi epsilon 0 R, big R. Do you agree? Yes? Now, what is the potential inside? Okay? This one you also find using integration. Okay? Inside, what is the electric field? Zero, reflex, very good. So electric field inside is 0. So if you take any point inside, let me call this point now A and this point B, and you write down VB minus VA equals to negative integral E dot dl, right? What happens is that inside this electric field is 0. Did you follow this? So what is VB? VB is equal to VA. What does it mean? It means that the potential inside is constant. All right? Everybody agrees with this? Yes? So if we plot it for conducting sphere, we have found that the potential is constant until you hit R over here, R, and then it falls down not quadratically with 1 over R. It falls down with 1 over R. Inside Q over 4 pi epsilon 0 R, outside Q over 4 pi epsilon 0 small r. All right?
John,
Tell me.
if this was a hollow sphere, the electric field was not zero inside it, right?
Let's do that one.
Hocam, isn't the R's like small one is the constant one or the constant?
Uh, so
Didn't we find
this is constant.
Yes.
So inside the potential is constant with this.
Okay.
Outside it falls down with 1 over r. So let's, for the sake of, yes. Yes, VR. This is the VR graph. For the sake of gaining some time, let's do the same analysis with a problem that we already solved. We have already solved the electric part of it. Let's use it to find the potential. Did you follow what I'm going to do? So, do you remember this complicated problem that we solved with few layers? So there was plus q here, minus q. We decided that this is the case, right? This is conducting shell. Like this part is fully material, this part is void, and inside there's a point charge. And the question is, find the potential everywhere. Okay? But this brings us to this formula being changed at each region. Remember, outside we have found that it was 3kq over r squared. Between, what is it between? 0, very good. And inside, kq over r squared. Do you remember this? We derived this, right? Everybody's with me? Yes? So what do? You basically start from the outside. Why? Because you, yes.
We defined v to be 0 at infinity.
Yes. So you define v to be 0 at infinity. That's why you start from outside. Because you want to do it with something that you already know. So your point B is again at infinity. And it is 0 potential over there. At a distance, let me call this A. You want to find the potential at a distance A. And you have a formula there which depends on x, let's say. Okay, this is r. Are we going to be confused? We are going to be confused. Shall I call this r prime? X is better, I guess. X is better. So I'm going to call this one r, this one x. What am I doing here? I am again integrating from a to b, and I'm integrating e dot dx. So vb minus va equals negative integral of e dot dx, dx, dr, dl, whatever you want to write it down, r to infinity. Any questions at this point? No? Is it too easy so that I should be moving even faster?
No.
No. Okay. That's a firm no. I like it. So this one is 0. VA is going to be our potential R outside B. And this one will be 3kq over x squared because of this. Okay? Alena, you are following? Yes? So 0 minus v at r greater than b is equal to negative integral r to infinity 3kq over x squared dx. We already know what this one gives, right? What dx over x squared with a negative sign r to infinity gives. It gives 1 over r. We already did this, didn't we? So let's use it right away. Was it positive integral? It was positive integral, right? Where is it? Okay, it was the positive integral. So this negative will take the other negative, and the positive integral gives you 1 over r. So v r greater than b is simply 3kq over r. Okay? We have just found the outside region. Let's go inside. Can someone tell me what I'm supposed to do to find the potential inside?
Integrate again.
Integrate again?
From the surface to a point inside.
Yes.
Conductive material.
Yes. So this time I will have a point A here and a point B here, right? And notice that the electric field is 0 inside because it's a conductor. So VB minus VA is integral of E dot dl or dx, whatever, negative sign, but doesn't matter because this is 0. So inside VB is equal to VA, meaning that the potential inside at any point here is going to be equal to the potential right at the surface. Do you see it? Why we don't go take it all the way out? Because the formula here is 0, then it changes to some other formula. So we integrate in the region where the formula doesn't change. Başak, right? Are you following all this? So Başak, V between A and B is simply V for R equals to B, which is 3kq over
Capital R.
B over B, because I have a formula for the outside and I'm applying the formula at the surface, which is at a distance B.
Isn't that capital R?
Yeah, we defined it as B. So far so good. One final region which is inside now. Now we are inside, going from, let's say, point A to point B over here. Okay, inside the electric field is like this. Okay. So let's do the same formula again. VB minus VA, but this time negative integral KQ over R squared, going from, x squared dx, going from R, which is inside, to up to A. Yes? Here we need to be careful. What is VB for this particular situation? What is VB? Hmm?
Potential of the surface.
Potential of the surface. It's this one, right? So VB is that one. Let's just write it down. 3kq over B. What is VA? That's what we are searching for, right? And now we need to take this integral and we need to be careful. So I have kq integral negative r to a dx over x squared, which is kq. Negative signs go out, so I have just 1 over x between a and r. Did you follow this?
Hocam,
Yes.
what is A here? What,
A is the inner radius.
like the whole radius, right?
This one is
The
A.
void's radius, okay.
Yes, the void's radius. So I get something like kq over A minus kq over r. So let's put everything together. V for r less than A is 3kq over B minus kq over A plus kq over r. So it's simply kq over r, but with a coefficient that would make sure that other potentials check out. Like right at A, this needs to cancel that one so that it's 3kq over B is recovered. Do you follow this? Because right at this edge, it has to be 3kq over B. Any questions, comments? Is it too hard? Başak says yes. Yes? Yes, it is hard. Yes, good. But doable, not impossible. Any questions at all? Yes.
Sınavda bununla alakalı nasıl soracaksınız hocam?
So the question is, what kind of questions should we expect in the exam? Just like this kind of questions. Like find the potential in this system. So what do? It's a very nice question because it's a combination of multiple chapters. First you find the electric field using Gauss's law. Then you take the integrals and you find it.
Or vice versa.
Or vice versa, giving
You can
potential.
find electric field from potential.
Yes, but we didn't come to that point yet. Good. You had a question? Good. Let me talk briefly about electron volt. It's just a unit, but it's an important unit. So let's talk about it.
Hocam, do you think that will we have some review time something like that, before the exam?
That's a good question. The only thing that I can propose is to do 4 hours on Thursday.
No.
No, fine.
Instead of 4 hours on Thursday, we could take back that 1 hour to Wednesday morning and do 2 hours. I mean, it depends on the class of the whole opinion.
We can do again 3 hours and it's in total 4 hours. And then we can do everything.
Where? When?
No, if we do the class on Wednesday morning and we can keep the schedule the same.
I can solve some questions and send it as a video if you want.
Okay.
I think it's better.
Yes? You are welcome. I haven't done it yet, so if I don't do it, you will hate me, but let's see. Let's see. I will do my best. Okay. So let's say you have a proton that has a charge plus E, right? Do you know this E, how much this E is?
1.602 times 10 to the 9.
O2'sunu bilemem. Times 10 to the minus
19
coulombs.
O2 bu arada var.
Of course, I'm sure. 1.6 times 10 to the minus 19 coulombs. This is the charge of a proton, or a negative amount of this is present in an electron, right? And let's say VA minus VB is 1 volt. So you can think of voltage as height for the positive charge. Like whenever voltage is higher, it's like a ball being at a higher hill. So if you let it go, it will go down to the lower potential. Do you see what I mean? So it will go from A to B, and it will gain this much energy, Q times delta V, which is 1.6 times 10 to the minus 19 coulombs times 1 volts. And we have a special name for this much energy. It is called the electron volt. So 1 electron volt is 1.6 times 10 to the minus 19 joules. Why do we care? Because the energies at the atomic scales are in this order. Like let's say an electron is jumping from one state to another. It might gain or lose 1 electron volt, 0.1 electron volt, 2 electron volts, like in this range. So we don't every time use 10 to the minus 19. Okay? Yes?
What is the reason behind the difference in precision or the values of electron and electron volt? Because if you check in maybe a behind cover or back cover of the book and check the values, they differ after a certain digit.
Do they?
They do. I mean, I can show you. It's yeah, I could bring you the book in this, but break.
Yes, during the break, let's look at it. Let's see what is the reason. Very good question. So, let me ask you, let me give you this example. Let's say you have an example. Like you have 2 plates. One of them is at 0 volts. The other one is, let's say, plus side of it, and we say that it's at 1000 volts. This is plus, but there is also a hole in it. Okay? I have an electron right in the middle. The question is, what is the kinetic energy of the electron in the in electron volts when it goes out? Do you understand the question? Yes? Any answers you want to give? Yes?
It is E times 500 volts if and only if the potential increases linearly.
It increases linearly. So you are saying that since it's right in the middle, this is the middle. I didn't say it, but you are right. It's at the middle of this, and so it will. The difference here is 500 volts, and the energy difference will be just 500 volts times 1.6 times 10 to the minus 19 coulombs. So the energy that it gains is 500 electron volts. Right? That will be the kinetic energy of this system. For some reason, yes, I remember now, this electron volt just appears in the middle of the text, and then we go back to the potential. Okay? So let's go back to the potential. I guess just to teach you electron volt, it's like an afterthought. Where should we put it? Just put it somewhere.
What
Yes.
is delta E in this question?
The change in the energy.
I thought it was electric field.
Oh,
was confused.
Okay, so let me just not write it like that. Let me write it as kinetic energy that
Use
it
the
gains.
formula VQ, right, for the energy?
Q times V, yes.
Okay.
The energy is charge times the potential difference.
So,
Yes,
how can the left side has zero potential?
zero potential.
0 volt, I mean.
Yes, by it being negative, you mean? Yes, very good question. So you see, potential is referential, so you have to call some place zero. And in this problem, we call that place zero. We could have called the middle zero, and that would be, this would be negative 500 volts. Okay? So even plus side could be, for some sort of convention, plus side could be negative 5,000. Yes. It's a matter of height. How do you define the height? With the sea level, or with respect to Everest, or with respect to Ankara for some reason? Okay. Example. So we go back to the potential questions. Here's a question, and this question is going to teach you how to sum up potentials due to multiple charges. So I have an equilateral triangle like this, and I'm wondering what is the potential at this point P due to these two charges. This distance is d. So how would you find the potential over there?
I would first calculate the individual potentials and add them up scalarly.
Yes. Does everyone agree? So this one tells you that potential is a scalar. Potential is a scalar. And you just find k q1 over d, and you add k q2 over d, and you are good to go. That's Vp. Of course, again, we are assuming here that the potential at infinity is zero. That's with respect to what we are calling this k q1 over d. Okay. There is only one exception, I guess, in my notes where we don't assume that the potential at infinity is zero. Instead, we assume somewhere else. And yes, there's a reason. All right. So we add it up scalarly, right? So let's do it for a ring. So you have a ring. There's a distance r. The distance is a. The radius is r. And you have just plus q here. What is the potential at this point P? Alena?
KQ
Yeah, KQ.
divided by a square cross r square parentheses 1 over 2.
Exactly. That's it.
Hocam, I would like to ask something. If the case was this, should we also say Q?
No.
Why?
Then you need an integral.
Why?
Why? Because not all charges are at the same distance. For the ring, all charges are at the same distance. I should note here that this is a ring.
Oh, I see. Okay.
Everybody understands? Yes.
And in that case, Q becomes dq, and we integrate over
Yes.
r.
Exactly. Exactly. Do you want us to do that? Yes.
Yes.
Why? Yes.
Perhaps we could get back to that after learning but I mean how to derive electric field from electric potential,
Yes.
and then it would be more useful.
Okay, let's do it now, and we will do the reverse. So what Ali is suggesting is that we can use these formulas to figure out the electric field and can compare it with what we have found before. So we will do that. So for this case, there is R, there is dr, there is this point P, this is A, right? So you just integrate K dq over A squared plus R squared square root. Do you agree? Everyone? Yes? So what is dq? dq is 2 pi r dr times q over pi big R squared, right? 2 q r dr over R squared. Everybody is happy? We have done this before. So this is integral k q over R squared integral 2r dr over square root A squared plus R squared. Everybody's with me? You agree? So we do u equals to A squared plus R squared. du is 2r dr. Our integral becomes du over u to the 1/2, and the integral becomes u to the 1/2 divided by 1/2. Do you agree with all this? Yes? Yes, tell me.
Actually, we did integration in the ring, right? It's just scalarly.
Yes, we are scalarly summing up the rings. Exactly.
Okay.
So this time we don't bother ourselves with directions. Okay? Any other questions?
John, can you tell how we found dq again?
VQ or DQ? DQ. DQ is, so DQ is basically dA times Q over pi R squared. Do you agree with this?
Yes.
What is dA? dA is like, there's a thickness to this ribbon over here, dr. So dA is 2 pi r dr. That's how we found it. All right. So what is the total potential at a distance a? It's basically kq over r squared times 2 times square root r squared plus a squared to be evaluated at 0 and big R, which gives you 2kq over r squared times square root of r squared plus a squared minus a. All right? Any questions, comments?
If it wasn't scalar, we need to cos.
Yes,
Okay.
but it is scalar. Okay?
Also, I mean, we started from 0, but to make it more general, we can start from some smaller value like a or small r. I mean, shouldn't we show it that way? I mean, we are calculating the potential due to a plate, a circular plate.
Yes.
But we can also do it for an annulus, and it would be more general.
For what?
Annulus.
What is annulus?
Disk içi boş.
Ah, okay. Going from A to B, right? Yes. That's a good midterm question.
I think there is such a midterm.
What?
I believe that there is such a midterm question.
There might be such a midterm question, yes.
Kitabında soru
Yes.
bölümü de var.
So it's, can you do it?
Yes.
Can you repeat the question, please?
The question was if it's annulus, like going from A to B, a disk, there's a disk going from A to B, right? Can you do it in the exam? Can you generalize what you have learned here to do it in the exam? I think you can, but you need serious practice to do it right. You can, but there might be some errors. Okay? I wish I could solve all possible questions there can be in the universe, but that's just impossible. At some point, you need to go beyond memorization and generalize your ideas to be able to do the midterms. All right, let's have a break. Sure.